Let me turn on Do Not Disturb mode so we don't get annoyed by. Right. So, a couple of things I want to talk about today are um, we've talked about doing certain graphics things, um, and what you guys have probably realized in the process is what's one thing that we haven't actually talked about yet in terms of programming in BASIC. Like if you think about what if we like back in 241 we were doing C or whatever, right? What were the sort of primitive building blocks that we built programs out of? Conditionals, loops, declaring variables and worrying about what data type they are. Okay, but what's missing? What have we not mentioned yet? A method or functions, right, in some sort of way. So we haven't talked about any of that yet, and that's what I wanted to hit today. I also wanted to talk about how you can, a method of storing data within a program as opposed to using a separate file. Okay, so for example, we could, you remember how we changed the character graphics to look different? We could store those numbers inside a program rather than in an auxiliary file. Both methods are certainly useful, but yeah. Okay, so I thought I'd start then with a discussion of variables and therefore subroutines or functions. Okay, so in BASIC, all variables are global. There is no concept of scope at all. Now, why is that maybe a good thing for there to be no concept of scope? Yeah, it's easier for beginners because trying to explain scope to somebody, I mean, think back to when you guys were in 111 or 101, for example. The first time you had to worry about scope, it was confusing, right? Now, you got over it, but if you're a beginner, that idea is not really all that clear. Okay, so in BASIC, or at least this version of BASIC, all variables are global in scope. What that means in terms of functions is that we never actually can, well, with subroutines, in this version of BASIC, you also cannot pass parameters around. And you don't need to because, well, all the variables are global anyway, right? So why have to worry about passing variables? Okay, so for example, let's just take what would be sort of um, a silly example of a subroutine that we could write. Let's just have it take in a number and square it. Okay, right. And in C or something, we wrote that, we had int, function name, parentheses, int, variable name, and then what did that do? It squared it, and then it returned that value, and all was good. And here it'll look different. Okay, so let me just choose a number. And sorry, let me change the cursor so it's easier for you guys to read. Oops, sorry. Okay, so let a equal 5, and then what I could do is do, let's say, line 30, print a, okay, and if I run it, then of course it prints it. Now, I haven't put in a subroutine here, and the subroutine call is where I'm going to put that on line 20. That's why I left space there. Um, so we'll see what the value of a is after it returns from the subroutine. Okay, so on line 100, how do I square a number? Well, let me just say multiply it by itself, right? And then 110, I'll do return. And then on line 20, I'll do this. Okay, so here's my program when all is said and done. The subroutine um, has to obviously be, it needs its own line numbers, right? Because it's still part of the basic program. But I also need to kind of put it down towards the bottom, if you will, in terms of the line numbers. And so often we choose, for this silly example, I chose 100 and 110 for it. But in a real program, I might choose a really big number like 1,000 that I know that the rest of my main program is never going to hit that many lines. Okay. Okay, so what's going to happen here is if I run it, line 10 will execute. A now has the value 5. Line 20 will go sub to line 100, okay? And then we'll hit line 100. What will happen to A? It will get squared. We'll hit line 110 and we'll return. And where do we return back to? Immediately after line 20, which in this case is line 30. Okay, so there is hidden from you, okay, a call stack that knows that when you hit return, where do you return to? The top or bottom, depending on your perspective, value on this hidden call stack. And that's how the basic knows that to return you to line, well, basically right after line 20 here. If you had lots of subroutine calls, you might be returning to different places in the code. How do you know which one to return to? Because all of that is stored in a stack. Okay, kind of like when we, in ARM, right, how did we keep track of our call stack, or how did we keep track of our breadcrumb system when we were doing function calls? We did pop things off the stack, but we were pushing the value of the link register to the stack. And then at the end of the subroutine, we popped the appropriate value off of the stack and put it back into the link register. And that's how we dealt with it, right? Basic is doing a similar thing, except it's all in software. There is no register or link register. And that subroutine stack, by the way, the deeper you go into a subroutine chain, the worse the performance gets. Like, it can get really bad. So nested subroutines, and hence recursion, which is, of course, all of our favorite thing, right, gets really terrible the further deep into it you go. Okay, so if I run this, what should happen? Oh, yes, okay. This is a thing that I've run into before. On line 40, we need to have end. Okay, and because otherwise you're going to get this error. Essentially, we have to define where the end of our main routine is so that it correctly interprets the go sub stuff. Okay, I've got a scowl and a question. Okay, Patrick, why are you scowling? Okay, what question do you have? Because 100, right? We have to tell it not just, we don't just say go sub, because then, well, which subroutine, right? Here we only have one of them, but there's no reason we couldn't have 10 of them, right? We have to know the line number of the subroutine where it starts. Yes. Okay. Yes, but then how does line 110 know to return back to here? I mean, I could have replaced line 110 with go to, but um, it's a function call, right? In particular, this will allow us to do recursion, right? Because with recursion, we don't know necessarily where to go back to, right? Yes? Okay, because of course, where are we going to go with this? If we can do this simple, stupid little function, what could we do? Yeah, we'll do the Fibonacci's. Of course, we're going to do the Fibonacci numbers, right? You guys should have been able to predict that from a mile away. Okay, however, before we do the Fibonacci numbers, okay, we need to talk about arrays of numbers because we will need that in our Fibonacci program. Okay, so first off, before we let's finish this. Any questions about how I set up this subroutine call? Okay. Now, not having the end statement is where you'll get the return without go sub error. Return without go sub error, you look at the code and you say, no, I've got both of them. What are you talking about, computer? It's not the most helpful error message, but that's usually what the cause is that you forget the end statement, which in a normal program with no subroutine calls, you don't need an end statement. Okay, it's optional. Okay, good. So, arrays. In order to set up an array, oops. Oh, by the way, you can delete a program and start over by typing new. I don't know if you guys knew that. No? Kind of clutch, right? Resetting machine also works. It doesn't matter. Yeah. Yeah. Well, because, and this is the brilliant thing, right? It's not like in terms of what's in memory, it's the same thing. It's just which character art you're pointing to. Yeah, okay. So arrays, right? So in Python or C or whatever, we can make an array, or I think in Python, right, it's called a list. But what is that? It's just a group of numbers or other objects sort of put together into some compound thing. Strings we could think of as being arrays of characters, but we could also do arrays of numbers. And the first thing that I'm going to do is actually allocate memory for an array. And the way I'll do that is with this thing called dim. Okay, so if I do, for example, dim, let's do a of 5, okay, a of 0, I have to do print. Okay, a of 1, a of 0, and so on are the entries in that array. So when I do dim of something, I'm just allocating space in memory for that array, but I'm not actually assigning any values to it. Okay, so for example, if I did this 10 dim of a of 5, 20 for I equals 0 to 4, or let's do 5, print a of I, next I, 30, end. I don't know what is with my keyboard today. Okay, so how many things got put into this array? Huh? A visitor? Hey, how's it going? Well, I had Rochella do it because it is, I mean, come on in. Yeah, so it's, and I know it's elsewhere in the building. Rochella said it's really hot. Down here, one of the problems we have is at least we're running these projectors most of the day and they put off a pretty good amount of heat, but okay. I don't think there's a class immediately after ours, so we end at just shy at 2:30. And I don't think there's anything in here after us. See if you can do anything. Yeah, I mean, I've thought about bringing a box fan in or two and putting one to bring air in and the other to take air out, but that's kind of a, MacGyver solution. Okay. All right. Thanks a lot. Because I've taught in this room for 12 years and it's never been this. I mean, you guys, we've had class in here how many times? And this semester, it's just, yeah, really hot. So, okay, thank you. Um, See, I told you that I'd talk to somebody. There's also some other air handling problems. So you guys have probably noticed that the doors are really hard to open. And you know why that is? Because in all the labs, all the fume hoods, they're exhausting air. And so there's a natural vacuum pressure that builds up. And that's why it's tough to open the doors. Um, yeah. And we don't really have this problem in Goodrich because none of the fume hoods in Goodrich are turned on. They're all because we don't really need them over there. We're not working with chemicals and stuff. So anyway, okay. So how many things did we end up with in our array here? 6, right? So it's I'm not sure why they did it that way. 0 to 5, you have 6 things. So what you're really defining is the last entry. And so you would think that a dimension of 5 would get you 0 through 4, but it actually gets you 0 through 5. I don't know why they did it that way, but that's what it is. Okay. So when you define an array, just think, right? If I try, for example, to print, well, what's A of 10, for example, what should happen here? We should get an error because we haven't allocated that into our array. Okay, so you should always allocate the array before you do anything with it. But I could, for example, do something like let A of 6 equal 10. That's not going to work, right? Because I haven't allocated that thing. Whereas if I let A of 5 equal 10, no problem. And then if I run my program again, oh yeah, because I didn't put it in the program. Oh, it's because what happened here, I reallocated. Well, but on line 10, I reallocated it. And so I wiped the A that I had already made. Okay. Um, and which is why it was 0 then. Okay. So anyway, does that make sense though? Right? Allocate the memory for the array either in or outside your program, and then you can put values in it, take values out of it, do whatever you want. Okay. Okay, good. So the right. Okay. So now that we've got arrays, let's talk. And I did kind of lie to you a minute ago. We can't actually do functions, but they don't really return. They can't return things. Okay. We'll come back to that in a minute. Because what I really want to do is to talk about recursion, everybody's favorite, right? Okay, now in order to do this, I'm going to put a web browser on the screen, and I'm going to put if we go to the C64 Wikis page on recursion, it gives the canonical example of this, okay? So what's the canonical example of recursion? What are the 2 canonical examples that we use? Fibonacci and maybe the factorial function, okay? So let's look at their Fibonacci code here. And I'm going to make actually a slight textual adjustment to what they did, which I think you guys will agree will make it more readable, okay? All right, so let me start a new program. And let me type this as they did. Okay, and I'll explain what all the things mean in a minute. Oops. stop and end are kind of equivalent. Okay, so line 10 allocates 26 numbers into an array. Basically, we can't go any further than that in terms of the recursion calls, so that's good enough. T equals Ti. So the variable Ti is a built-in one that you're not allowed to use. So you can't have anything that starts with Ti as one of your variables. Ti will get the current system time. And what we're doing here is if I compute the current system time when I start the program and subtract it from the current system time when I'm about to finish the program, that will tell me essentially how long it took for my program to run, okay? Which will allow us to have some sort of measure of the complexity. And of course, what do you expect for Fibonacci's? What happens if I ask for Fibonacci of 5 versus Fibonacci of 10? It's going to get progressively slower the further I go because I'm doing a deeper set of recursive calls. Okay, now, so line 10 is just allocating the memory and getting the input value from the user. 20 is stamping the clock. 30 is calling the recursive function. When we come back from the recursive function, lines 40 and 50 will print what the value is and how long it took us to compute it, and then quit. And then the subroutine business is going on at line 100. Okay, so what's the base case for Fibonacci? Yeah, so if you plug in anything basically 0, 1, or 1, but like I like to start the Fibonacci's with 1. So Fibonacci of 1 is 1, Fibonacci of 2 is 1, Fibonacci of 3 is when the recursion starts. So for values, input values less than or equal to 2, the answer is 1, and on here the answer is the number f for Fibonacci. And I'm going to then return and print, and then we're done. Okay, so that handles our base case. The other two cases are a little bit weird. Okay, so n equals n minus 1 on both line 110 and 120. Well, let's think about that for a minute. When I do Fibonacci of 5, what do I have to compute? Fibonacci of 4 and 3. And so n equals n minus 1 is getting me the numbers 4 and 3 for the two recursive calls. Okay? Then go sub 100 is just calling the recursive function. And then the stuff after the go sub 100 is just, well, what do I do when I'm finished? Okay? What I'm going to do is add 1 to the value of this number m, which is which index I'm going to be inside of an array. And so all of these previous answers, I'm storing them in an array called S. Okay? And then I'm saying, okay, make the mth entry of the array the current answer F. The next one is F is the current value plus whatever's in the array. That will get me the two answers put together. And then line 130, this one's weird. I need to subtract 1 from n and then restore n to back what it was because I don't have local parameters, right? I can only do global things. So I know that looks weird, but there it is, okay? Now, look at their version of the code, which is almost identical to what I typed. But what did they do? What's the difference? They don't have M, but what do they have? S. So look at their array, or look at line 110. They set S equal to S plus 1, and then S of S equal to F. Okay, this drives me bonkers because what they're doing is using the letter S as an integer in one case and as an array in another case. And because those are different data types, you can actually use the same name. However, is that wise programming? It seems dangerous, but more importantly, it's hard to explain. Okay, so I need to go find who wrote this and beat them over the head with the 2x4 that's in my office, right? Because it's confusing. When you first look at that, you're like, wait, what? Okay, does that kind of make sense? Yes. So, hmm? uh, it, oh, okay, good question. If S is not defined, what is its starting value? Right. Okay. So I could have added let S equal 0 to line 10, for example, just to initialize the variables at 0. But if they're uninitialized, their default value is 0. Okay. All right. So ready to run it? See what happens. All right. What value do you want to do? 12. Let's not do that high. Let's start with the base case. Oh, crap. What did I do? Oh, I forgot the word if. Sorry. Oops, syntax error in line 50. Okay, so I probably made a typo here. Print calculation. Oh, I've got print twice. Yeah, okay. There we go. Oops. Okay, so Fibonacci of 1 is 1. Is that correct? Fibonacci of 2 is 1. Fibonacci of 3 is 2. Oops. 4. All right. And I think somebody said let's do 12. Okay, is that correct? Yeah, it is. Okay. So, right. So as you can see, right, the recursive calls get progressively worse the further down you go. And in fact, the limit, and they actually tell us what the limit is, the last value you can compute before things overflow is 23, and it took 16 minutes and 12 seconds. Okay. All right. Now we give the Fibonacci's as one of our canonical examples of recursion because, well, it comes up plenty in math, right? And it's sort of a nice example. But would you ever actually code Fibonacci's recursively, except when your evil professor is making you think about recursion? Of course not, right? What's the much better way to do it? Yeah, do it iteratively, okay? And there's a couple, obviously, ways to do that. So doing the Fibonacci's iteratively is far more efficient, okay, than doing it recursively. But also with the recursion, notice we never memoized here, right? So what does memoizing mean? Yeah. Yeah, exactly. So for example, if I wanted to do Fibonacci of 5, I need to do Fibonacci of 4 and 3. But to do Fibonacci of 4, I need to do Fibonacci of 3. Do I need to do Fibonacci of 3 twice? Or could I do it once and remember that answer? Right? That's called memoization. Uh, if you can do that, right, and implementing it's sort of another problem. But in the case of the Fibonacci's, what's just the better answer? Do it iteratively, right? It's much faster that way. Okay, so you can expect some sort of interesting recursion homework. How about that? Yeah, wouldn't that make you happy, Luca? Mm-hmm. Yeah. Yeah. Okay, so you can do functions, and here's how you do those. Well, first off, any questions about the recursive stuff? Okay, and this will, you just have to sit down and play with it, and, right, so what would be a good, well, if I've given you guys the Fibonacci's as the example, what would be a good exercise for you to do instead? You guys are killing me. All right, what would be a good example to do, or I mean, a good exercise? What would be an excellent exercise to do? Hmm? You can't do cosine recursively, huh? Yeah, factorial would be a good one. Or if we can do the Fibonacci's, has anybody ever heard of the Tribonacci's? Well, it's just where you add the previous three terms instead of the previous two. Yeah, you like the factorial idea better? Okay, maybe that's a good one. Yeah, so think about the factorial. Okay, so what's different about the factorial versus Fibonacci? Huh? You're multiplying by the previous ones, but then also what else? You only multiply by the previous one, not the previous one and the previous two, right? So Fibonacci uses addition rather than multiplication, but it's in some sense doubly recursive. Factorial is only singly recursive, right, in that each call only makes one call, but you're multiplying instead of adding. That's why the numbers get so big so quickly. Okay, so Fibonacci sounds like a great thing to do. And you know what would be another great thing to do if you're going to do it recursively? How else should you maybe do it? Yeah, and if only we had this time variable that we could use to sort of measure the relative time or efficiency between the two methods. Wouldn't that be great? Yeah. Okay. So stay tuned for a really exciting new assignment on Canvas coming to a page near you. Okay. Functions. Um, we can actually do functions. All right. And let me do this in the following way. So let me just say, for example, def 10, def function, name a function, and variables it's going to take. So let me call it myfunc, and it's going to take a variable, let's call x, and what is it going to do? It's going to return, let's just pick this number. This is there. Okay, so here's the function I've written. So what have I defined here? I've defined a function called myfunc, and what variable does it take? A variable x, and what does it do to it? It just adds 7, okay? So this is like, I want to think about this more as, it's not really it's not quite a function in the same way that when we wrote functions in C were, right? Because how many lines of code could a function be in C, or Python for that matter? As many as you wanted, right? But look at the structure of how I have to do it here. I have to return a number, right? So the functions that are like when I make a function with def fn, it's really something that takes in maybe several numbers, but it can only really return a number, right? Because of the equals part. So maybe a better way to think about this is it's not truly a function in like the C or Python case. It's sort of a math function, right? So in the same way that I could have sine of x, I could maybe define my weirdo version of sine of x, say. Okay. But I'm also very limited in terms of how much code I can write, because how many lines can I fit, or how many characters can I fit on a given line of a basic program? At most 80, right? That doesn't give you a whole lot of room for stuff. Okay. So you would probably not use this too much in practice, or at least not functions the way they are in Basic V2. Other dialects of Basic are much more robust in this sense. Okay. Okay, so is that all right? Yeah? So let's run this and see what happens. And hopefully I didn't screw anything up. What did I do there? Okay, why did that not work? Oh, I think. Nope. No, why is that not working? Okay, hold on. Let me make sure I didn't screw something up. Oh, duh. God, I'm sorry, guys. There we go. Okay. So what I forgot is you can't just use the name of the function. You have to prepend it with fn for function name. Is that okay? We never had to do that in C, but you do in BASIC. Um, so no, I don't have to say let. That's optional. It's just a habit I've gotten into. So now, if we think about the reason why, actually, it makes sense that they would have done this. Because when I was trying to print my func of x, what BASIC was thinking is that I had an array called my func, or something like that, or an array called my, because really only the first two letters matter. And that's not what I'm doing, right? I'm calling the function named myfunc, and in order for the basic interpreter to know that, I need to have fn in front of the name of the function that I'm calling. Okay, does that make sense? Yeah, and I'm going to forget this. This is the problem when I teach Python in the morning and this stuff in the afternoon, that I'm going to be like, I can't tell you how many times I've been putting semicolons at the end of lines when I'm teaching Python, because it's just reflex. And yeah, okay. Um, yeah, so the functions here, probably not all that useful, right? Go sub is, I think, maybe a bit more useful, because how many lines can a subroutine for go sub have? Is there any obvious limit? I mean, it can't be more than you have memory to store, but if you need 10 lines for a subroutine, that's fine. Whereas this function thing, in some sense, can only be one line. Okay, so I don't think the functions are super helpful, but the go sub stuff certainly is. Okay, good. The other thing, of course, is that functions can't be recursive, whereas go sub calls can be. Um, yeah. Um, okay, so there's that, and then the next thing I wanted to talk about was data statements. Okay, and this gets used with the uh, the read instruction, which is kind of like the get instruction, but a little bit a little bit different. Okay, so let me go to here and just remind myself. Here we go. Okay, so let me make a new program. All right, and I'm going to put on line 100, I'm going to put some data statements. Okay, and on line 10, I'm going to say for I equals 1 to 4, okay, read A, print A, next I. Dang it. Okay, so what this does is, so notice at the very end of the program, it doesn't have to be at the end, but that's sort of the most logical place to put it just for your own sanity. I have typed here data followed by comma separated values. Okay. Now these comma separated values, in my case, I've picked whole numbers, but those are really floating point numbers in terms of internal storage. They don't have to be. I could have data that has strings also, or arrays even, right? But I'm just, for sake of example, going to do it with just 5, 10, 15, and 20. Okay, great. If I run that, then each time my loop runs, what's really going to happen? I'm going to read A and print it. Okay. Now, where was the variable A ever defined? Did I ever define the value of A? No, but the read command will do that. Okay. So what is the very first piece of data in my list of data on line 100? 5. Okay. So when I hit read A, Basic is going to say, all right, what's the first piece of data? And I'm going to assign the value that I find there to the variable A. So A becomes what? And then that gets printed. Yes? Okay. Then when I come around and I iterate again, Basic keeps track of, I've already used this one. And so when I read A again, what does it give me now? The 10 instead of the 5. And if I do it again, it'll give me the 15 and the 20. Okay, how is this similar to the get instruction? Like, how have we used get? Well, let's do in particular get pound. Right. Yeah, it steps character by character or byte by byte, they're equivalent in this case, on a file access, right? So for the word or character counter, right, how are you accessing one after the next character? You're always doing get hash mark 1, and then in this case, because it's strings or characters, a $sign, right? And so what keeps track of where you are in that range of characters? There's sort of a hidden pointer that the disk drive keeps track of it for you. In the same way, Basic keeps track of the pointer to which data entry you just used. And it's always ready to point to the next one to be gotten, or in this case, read. Okay, does that make sense? Yeah? Now, it is possible to actually go back and start over again. Okay, and you can do that with this the instruction called restore. So let's look at that. Um, okay, so let me do this. Okay, let's just see here. Am I done? Yes, okay. Oops. Let's see, I need to do, okay, hold on. I don't think doing this in the loop, let me start over. I don't think doing this in the loop is going to be as illuminating as I thought. Okay, so let's do for I equals 1, 2, 4, read A, print A, next I. And then on line 20, I'm going to hit restore. Line 30, I'm going to do basically copy. Okay, so I get that. So basically, restore nukes that pointer and takes it back to the beginning. Okay. Can't think of any particular reason why you might want to do that off the top of my head, but you certainly have that ability. Okay. With the get thing, is there something equivalent? Well, if you wanted to reset the pointer back to the beginning of the file, what could you do? Well, okay, but restore only works for the read thing. It doesn't work for file reading or getting, right? Yeah, but that's going to get the next character. So how do you reset basically the get so it goes back to the beginning of the file? You guys are going to kick yourselves when I say it. Hmm? Nope. Because you don't know where this pointer is. You don't know what variable it has attached to it, right? It's not user accessible. No? Any ideas? Why don't close the file and reopen it? I mean, that'd do it, right? Yeah? Well, great. There you go. Close the file and reopen it. Now, maybe there's a more elegant way to do it, but that certainly would work. Okay. I'm not aware of an equivalent to restore, but for the file pointer, file access pointer. There probably is in machine language, right? Because in machine language, we can start talking directly to the hardware, and in particular, if we're to talk directly to the disk drive. Uh, because, actually, I should mention, if I haven't already, what's inside the disk drive? What's in there? I mean, yeah, there's the spinny thing, right? But what else is in there? Huh? The disk itself. I don't have a disk in my floppy drive. What's in it right now? What is inside the floppy drive? There's the spinny stuff, and there's a processor, and RAM, and ROM. In fact, the disk drive is, in a sense, its own little computer. Now, it's its own little computer whose existence is to do what? Yeah, just to read and write stuff to and from floppy disks, right? Read it and send it out over the cable to the computer and accept data from the computer and put it on the floppy disk, right? And accept commands from the computer for how to do that. So the disk or the drive itself is its own computer. And in the same way that we can program the Commodore in machine language, or BASIC for that matter, we can program and tell the drive to do things. We'll have to do that in machine language, but we can send instructions over to the drive and it will do them. We have to know what good instructions are, or else we're going to screw up the drive, right? If we want to do something useful with it, we have to know its language, but we can do that. And in fact, did I tell you guys what people used to do with math problems back in the day? Yeah, what did I tell you guys about disk drives? It's got a 6502 chipped in it, just like the Commodore itself. In fact, it's even clocked at the same 1 megahertz, right? Which is kind of overkill for a disk drive, but fine for a computer. And so if you were really good with machine code, you could send an entire program over to the disk drive that would live in disk drive's RAM. It had its own RAM. And you could have the processor do calculations using that piece of a program. And so people would turn their disk drives into basically math coprocessors and therefore be able to do twice as much math in a given amount of time, right? It's kind of bonkers, isn't it? You guys don't remember me telling you about that? Now you do? Okay. Now you remember? I remember. No? Yeah. Yes? No? Okay. All right. So where would the data statements, where would this maybe be useful? Okay. And maybe what's an alternative to having data statements? And what's the utility of them? What's good about them? What's bad about them? How do I read them? Or how do I have to read them? I have to read them in order, right? So if I read and then read and then read, how am I getting these values or whatever they are? In the order that they appear in the data statements. Okay, and if there's more than one line, it'll just continue to the next data line. So for example, let's say that I had, let me add line 60, and then let me change line 10, oops. Right? So if I have multiple data lines, it'll just continue to the next one if I've exhausted the data that's on a given line. Okay? And the file or the basic interpreter basically keeps track of where I am in the data reads automatically. I can restore it and go back to the very beginning with the restore thing, but I don't have sort of random access in some sense, okay, which is maybe mildly annoying. Okay, so would I want to do like I wouldn't be able to like store a spreadsheet kind of thing this way because there's no way to necessarily be like, you know what, I need the 10th thing in the list. Well, sorry, you got to read the first, second, third, fourth, and so on before you can get to the 10th. It's not really all that helpful, is it? Okay, but for a linear data structure where you do need to read them in a row like that, that could be really good. For example, what about if you wanted your program to change the character graphics and then when it was finished, change them back? You could store those new character graphics in the data statements, and then when your program's ready to finish, reset them, right? And since the data, sorry, for the characters, those bytes have to go into a certain order, well, then the data statement's great because you're just storing them in a linear order. That's fine. Okay. This would also be useful when we do music. Maybe next week we'll talk about the sound chip on this thing, or Friday or Thursday, whenever. What's today? Tuesday? Yeah. So we could store note information for a song. Um, the downs, or what maybe one of the other upsides to these is where is the data stored? It's stored in the same file as our program. Is that the good utility there? So what's the good utility of that? How many files do we have to worry about? Just one, right? The downside would be what happens if we have a lot of data, like a lot of data? Yeah, how much space can we fit, or how much space do we have for basic programs? Yeah, 39K basically when you power on the system, right? Well, how much can the disk drive fit? How much can a single side of one of these floppies fit? That's way more than that. 170K roughly. Okay, so that's way more than we have RAM, yes? Okay, so storing all of the data in the program is probably not a wise thing. The other reason is, do you need to store all of the data all at once all the time? Or would it be better to load data in as you need it and clear it when you don't? Which means using external files, right? Okay, so you can do effectively this data statement. I think we talked about with the user files, um, which are essentially comma separated values, like a CSV file, right? They're kind of like data statements. They're just external to the program instead of being internal. And then the record thing would be the other, which is the fourth data type. There, I think you can do random access, which would be useful if we were trying to build like a spreadsheet or something. Okay, and do computations. Okay. Um, okay. So let's see. Anything else? The data statements, recursion, functions and subroutine calls, um, reading and restore. I think that's what I wanted to hit today. Any questions, preguntas, or fragens? No? It's getting hotter by the minute in here. I don't know about you guys, but I am just dying. Okay. All right. Well, I guess let's quit a little early. How about that? Yeah? All right. See you guys on Thursday.